In this section, we discuss independent component analysis. Assuming that a vector x is synthesized by a linear combination of independent components. X is known. The matrix A is the mixing matrix, which is unknown. And the vector S containing independent components are unknown. The unmixing matrix W can be estimatable, and the vector S containing the independent components is also estimatable. So without knowing the mixing matrix A, we can still estimate the independent components. If you look at one component and let Y be the product of W transpose and X, and X is actually the product of the mixing matrix A and the independent components in the vector S, you get to this, and this is a linear combination of independent components Si. So by the central limit theorem, the sum is more Gaussian. It is less Gaussian when it is equal to one component of S. So maximizing the non-Gaussianity of Y gives us one independent component. Kurtosis can be used to measure the non-Gaussianity. If Y is normalized, then the variance of Y is equal to 1. The expected value of Y is equal to 0. So the expected value of Y squared is equal to 1. So from there, we get to another form of the kurtosis. Using the Lagrangian method, we can get the iteration formula of the wave vector to maximize the kurtosis. Another way to measure the non-Gaussianity is to use Negentropy. As we have known, entropy is a measure of uncertainty and a measure of the information of a random variable. Negentropy is defined as the difference between the entropy of the variable and the entropy of a Gaussian variable with the same covariance. Similarly, we can find the iteration formula for maximizing negentropy. This is the algorithm flowchart for independent component analysis. At first, the mean is subtracted, and then the data is whitened to make the variables uncorrelated. Then we initialize a vector Wi, and then we start a loop, iteratively update the vector Wi, following the iterative formula for kurtosis or negentropy. The vector Wi needs to be orthogonalized with previously found weight vectors using Gram-Schmidt orthogonalization. Once we find a weight vector, we store the vector as a row in the matrix W. The next few slides provide additional information regarding pre-processing and orthogonalization and normalization. Projection can be done using independent component analysis by taking the matrix product of the unmixing matrix W and the vector X, or can be done using both principal component analysis and independent component analysis. A smaller set of eigenvectors in WPCA helps reduce the number of dimensions in X.